Imagine a shield of light, silently intercepting incoming threats with pinpoint precision and at a fraction of the cost of traditional defenses. This vision is rapidly moving from science fiction to reality with the advent of advanced laser weapon systems. Among these pioneering technologies is the Iron Beam, an experimental project developed by Israel, designed to offer a revolutionary approach to air defense. The Iron Beam is engineered to engage a variety of aerial targets, including drones, rockets, and mortars, presenting a versatile and potentially game-changing addition to modern defense capabilities. Its strategic intent is to complement, rather than replace, Israel's existing Iron Dome system, an advanced rocket-launching defense mechanism recognized globally for its effectiveness. While the Iron Dome launches expensive interceptor missiles, the Iron Beam promises to provide a highly cost-effective alternative, significantly bolstering Israel's protective capabilities against diverse regional threats. However, like any nascent technology, the Iron Beam faces several technical challenges, including limitations in range and sensitivity to atmospheric conditions. To overcome these hurdles and accelerate its development, Israel is reportedly exploring cooperation with the United States, leveraging expertise that could enhance the system's performance. At its core, the Iron Beam system comprises three main components: a powerful laser gun mounted on a swiveling unit, a sophisticated surveillance system to detect and track incoming threats, and a centralized command center where operators direct its operations and make crucial engagement decisions. Officials involved in the project have indicated that the laser gun emits a formidable beam consuming approximately 100 kilowatts of power. To put this into perspective, this is a substantial energy output, roughly equivalent to 100 times the typical electrical consumption of an average household in the US. This immense power is critical for delivering the destructive energy needed to neutralize fast-moving and potentially explosive targets. Visual evidence released by defense authorities demonstrates the system's capability, showing the laser successfully intercepting and neutralizing an incoming rocket, providing a tangible glimpse into its operational potential. A primary driver behind the Iron Beam's development, and indeed its most compelling advantage, is the potential for significant cost savings. Military analysts suggest that integrating this laser weapon into the national arsenal could substantially reduce the reliance on the more expensive interceptor missiles used by the Iron Dome. The economic disparity is stark. A single interceptor missile fired from the Iron Dome can cost upwards of $50,000, or even more, depending on the variant and situation. In profound contrast, statements from high-ranking officials have suggested that the Iron Beam could achieve a similar interception for as little as $2. This dramatic difference in cost per engagement could fundamentally alter the economics of air defense. Defense engineers and military analysts highlight two critical advantages stemming from this design. Firstly, the dramatically lower cost per successful engagement means that a nation could intercept a far greater number of incoming threats without depleting its defense budget at an unsustainable rate. This is particularly crucial when facing adversaries who employ low-cost, massed attacks. Secondly, the elimination of physical ammunition offers a profound logistical advantage. Conventional missile systems require complex and resource-intensive processes for production, storage, transportation, and maintenance of interceptor missiles. An ammunition-free laser system, on the other hand, operates as long as it has power, thereby alleviating substantial logistical burdens and production strains, ensuring a more sustainable and continuous defensive posture. Despite these promising advantages, the Iron Beam faces several technical hurdles that need to be overcome before widespread deployment and optimal operational effectiveness. These limitations include its relatively short effective range, a notable susceptibility to adverse weather conditions, and a comparatively lower engagement rate when confronting multiple, simultaneous threats. One significant vulnerability is its sensitivity to environmental factors. The system's intricate sensors, which are crucial for detecting and tracking targets, along with the laser beam itself, can be adversely affected by challenging atmospheric conditions such as rain, fog, heavy cloud cover, and even dust. This means that the Iron Beam might not be fully operational or as effective during colder, wetter months in regions like Israel, potentially necessitating a greater reliance on the Iron Dome during such periods. This intermittent operational capability creates a potential window of vulnerability, underscoring the need for a robust, all-weather solution. Another inherent limitation is the beam's effective range. As the laser travels through the atmosphere, its power dissipates due to a phenomenon known as the bloom effect. This occurs when the high-intensity laser beam interacts with atmospheric particles, including water vapor, dust, and aerosols. This interaction causes the beam to widen, defocus, and lose intensity, eventually becoming too diluted to effectively damage a target. The consequence of this atmospheric attenuation is a significantly restricted maximum distance at which the ion beam can maintain sufficient power to neutralize threats. Unlike missile-based systems that rely on kinetic energy or explosive warheads, the continuous energy transfer of a laser is highly susceptible to these atmospheric interferences, limiting its reach. Furthermore, the speed at which the ion beam can neutralize objects also presents a challenge, particularly in high-threat scenarios. While the laser beam itself reaches the target at the speed of light, its destructive mechanism is not instantaneous. It requires a dwell time, a period during which it continuously pumps energy into the target, to cause sufficient damage, such as melting the structure or igniting explosives to trigger an explosion. This process can take a few seconds. While seemingly short, this dwell time is a critical factor when dealing with saturation attacks involving numerous incoming rockets launched in rapid succession. The need to maintain the beam on one target for several seconds could hamper the system's ability to swiftly engage multiple incoming rockets simultaneously. This limitation suggests that the ion beam, on its own, might struggle against massed attacks similar to those involving numerous rockets fired from various positions, where rapid target acquisition and neutralization are paramount. Despite these considerable challenges, Israel remains committed to advancing the ion beam, with officials indicating potential deployment in the near future. This initiative is part of a broader global trend, as major powers such as the US, Russia, and China are also investing heavily in developing laser-powered weapon systems. These nations recognize the profound potential of directed energy weapons as a cornerstone of future military capabilities, capable of offering precision, speed, and cost-effectiveness that traditional munitions cannot match. The development of such weapons signifies a paradigm shift in warfare, moving towards energy-based weapons and igniting a global race to achieve superiority in this domain. The US Department of Defense, in collaboration with leading defense contractors, is actively testing advanced laser systems, some based on similar technology to Israel's ion beam. Reports suggest that some US-developed technologies are capable of generating 300 kilowatt lasers, significantly more powerful than the current ion beam. The power output directly correlates with effective range. Higher kilowatt systems can strike targets at greater distances. While the precise range of laser weapons can vary based on target type and atmospheric conditions, initial estimates suggest American lasers could achieve ranges twice that of Israel's current system. However, even these advanced laser systems currently possess a significantly shorter range compared to traditional interceptor missiles, such as those used by the Iron Dome, which can engage targets up to 43 miles away. This underscores that despite advancements, laser technology is still in a developmental phase, particularly concerning long-range engagements. Given these inherent limitations, Israel is actively seeking collaboration and support from the United States to enhance the ion beam's capabilities. During a state visit to Israel, a US president was reportedly shown the ion beam and publicly affirmed the United States' unwavering commitment to Israel's security. This commitment includes partnering on cutting-edge defense systems, specifically mentioning support for both the proven Iron Dome and the new laser-enabled ion beam. Furthermore, legislative bodies are reportedly considering allocating additional funding, potentially $1 billion, to support the Iron Dome, a system the US Army has also been evaluating at its military installations. Any potential cooperation on the ion beam could significantly accelerate the maturation and operational deployment of laser weapons on the modern battlefield, transforming theoretical concepts into practical and widely deployable defensive tools. This partnership is vital not only for the security of allied nations but also for the advancement of directed energy technology globally. In conclusion, the Iron Beam represents a significant leap forward in defensive technology, offering a tantalizing vision of cost-effective, ammunition-free interception of aerial threats. While it currently faces notable technical hurdles related to weather susceptibility, limited range due to atmospheric effects, and the dwell time required for target neutralization, the potential for its seamless integration alongside existing systems like the Iron Dome is immense. Its ability to drastically reduce the cost per engagement and alleviate logistical burdens makes it an attractive proposition for modern defense. With continued research and development, particularly through international cooperation, the Iron Beam could evolve into a pivotal component of future air defense, fundamentally altering the economics and logistics of protecting critical assets and populations against increasingly sophisticated and varied aerial threats.